Our next speaker is Weinan E, who is professor in the Department of Mathematics and the program in Applied and Computational Mathematics at Princeton University. He will speak on a mathematical theory of solids from atomic to macroscopic scales. Weinan?
It's a true honor to be speaking here on this very important occasion. So I'll be speaking about how one would try to build a mathematical theory of solids. And I'll try to make this general. And also, so I guess in half an hour, what I'll be able to do mostly is just to describe what sort of the issues one has to address and what are the kind of approaches one might take. Now, to begin with, let me make a comparison between fluids and solids. In fluids, there is a fundamental mathematical model that's very well accepted, and this is the Navier-Stokes equation, where this is the system of nonlinear differential equations. V is the velocity field of the fluid, and this is a very well accepted model. As a matter of fact, it's brought to some prominence as one of the millennium problem, the regularity issue of this model. From a physical viewpoint, it describes the fluids very well. It's quite a challenge to think of a situation for which this model would not be valid. So as a result, you can study fluids without knowing much about fluids. You just have to think about this problem here. Now, solids. What is the situation for solids? So first of all, for solids, instead of looking at the velocity, you look at the deformation. You look at the displacement. So if you look at here, say you have a configuration that's before deformation, and you have a configuration after deformation, and then U is the displacement field. So that's macroscopically, that's this object you want to study. So what would be a fundamental model of solid? Now there is a linear elasticity, which I wrote down there, and that is a rather simple problem, at least by current standards, but that has rather limited validity. And then you can think about nonlinear elasticity, which presumably describes larger deformation, but then here already this function W is a bit of a problem. What is the function W is a bit of a problem. And then there are lots of solids has plastic behavior. So you have to think about plastic models, plasticity models, which I wrote in dots because there are so many of these models. So it's not clear that there is a fundamental model of solids. And there is good reason why. Because solids, compared with the fluids, are much more multi-scaled and heterogeneous. I'm going to explain what that means. First of all, everything is made up of atoms and electrons. In the case of fluids, they're also made up of atoms and electrons. But for various reasons, you really don't have to think about the atoms and electrons, what they're doing when you think about fluids, when you try to describe fluids. All the information about what the atoms are, what the electrons are lumped into very few parameters, namely viscosity, in the case of incompressible fluid, the equation that I wrote down earlier. Solids is a different story. First of all, solids at the smallest scale is a crystal. And there are different crystal structures. So here I'm drawing rather simple crystals. So this is a cubic crystal here, and this is a body center cubic. So you take a cube and you put an atom in the center of the cube. That's body center cubic. And then some more. Let me show two more pictures. This crystal this is the face center cubic, and this other complicated thing is supposed to be a diamond lattice. I'll explain diamond lattice later, but in more detail. So at the small scale, there are crystals. And what the crystals are, what crystal structure a solid takes, has a larger impact on the macroscopic behavior of the solid. So that's one thing. And second thing is that these crystals are never really ideal crystals. They have defects. Zero-dimensional defect, for example, would be a missing atom. So that's a point defect. And there's one-dimensional defect, which are called dislocations. That's a rather complicated object. And there are also two-dimensional defects. So there's a hierarchy of defects in these crystals. And when you look at a macroscopic solid, that this thing here is not a crystal, certainly. It's lots of randomly oriented crystals packed together. And that's the macroscopic level. So there's this hierarchy of structures. So let me give you sort of a cartoon here. This is the broken Titanic. And you look at carefully here, there's a crack, right? There are lots of cracks, but look at this crack in here. This is taken from the webpage. I didn't draw this. So this crack here is, if you blow it up, may look something like this. As a matter of fact, this is the atomistic simulation. If you look carefully at the crack tip, you'll see the atoms. And if you look at carefully still, you'll see that the atoms here are pretty crystalline. They're in the lattice. And these red atoms are in the wrong position. So these are the defects in the crystal. This hierarchical structure is important for understanding solids. Now, it's not true that there's not a fundamental model. There is. That's the quantum many-body problem. You can write on the energy in terms of all the positions of atoms. These are the R's. These are the R's are the positions of all the atoms, 10 to the 20th of them, in there. The energy has two parts. One is due to the repulsive Coulomb interaction of the nuclei, and the other contribution comes from the electrons. That has to be computed by solving the Schrödinger equation, the many-body problem. So in principle, you can solve this equation and then determine everything about solids. As a matter of fact, Paul Dirac pointed this out. He says that large part of physics, he didn't say all of physics, he said large part of physics and the whole chemistry, he was sure the chemistry is completely known because you just have to solve this equation. The only problem is that this equation is too complicated to solve. So what should we take as the starting point? When we try to build a theory starting from atoms and electrons, what should we take? So first of all, we can take quantum many-body problem in case that's not too complicated. In some cases, we have to look at it at that level. But some other cases, you can get away. You can get away with the simplified models, such as density functional theory, which is becoming popular nowadays, even in the mathematics community, because of the '98 Nobel Prize. And there is a still more simplified model called tight binding quantum mechanics model. So these are quantum mechanical in origin. And then you can take these classical potentials. Sometimes they're not so bad. So one of the most well-known is the Lennard-Jones. And I wrote on the Lennard-Jones. In that case, the atoms only interact pairwise, and the potential depends only on the distance, and the distance takes this 12-6 form. And there are, as a matter of fact, very few solids are described well by this potential, but there are other more complicated potentials, such as embedded atom model, which are pretty successful. So you can take these as the starting point. Now, when we think about building a theory for solids, there are two important themes that I have to keep in mind. One is sort of a general geometry. And I already explained solids at the atomistic scale are crystals. And what crystal structure they take is very important. Now, the crystals themselves are not so complicated to study. It's the crystal defects that are important, that are non-trivial to study, the defects in the crystals. So let me show you some of these defects, how they're related to the particular crystal structure. So first of all, let me look at this, the phase center cubic. So phase center cubic lattice is a closed packed lattice. The other closed packed lattice is hexagonal closed packed lattice. So that by definition must be closed packed. But why is phase center cubic also closed packed lattice? This might not be so obvious at the first sight. And the way you look at it is look at diagonally and look at how the atoms are arranged in the planes which are orthogonal to the diagonal direction. And then if you look at, for example, the planes which are made up by these red atoms, you can see they're a hexagonal. They form a hexagonal lattice, which was the lattice drawn on the board a few minutes ago. So hexagonal lattice are the closed packed lattice in 2 dimensions. And then the phase center cubic lattice is just the packing of these hexagonal lattice, planes of hexagonal lattice. And the packing has a period 3 packing. Namely, if you look at this corner here, that's in one layer. And the second, this is the A layer. The second layer are the red atoms, which second layer are the B layer, which are these heavy circles, and then the third layer, the C layer, and then you come back to the A layer. So this is the period 3 packing of hexagonal triangular lattice. Did I say hexagonal? These are triangular lattices. Maybe I said hexagonal. In contrast, the HCP, the hexagonal close packing lattice, is AB packing. It doesn't have to say, imagine, delete all the C layers. That's AB packing. So this is the hexagonal, this is the FCC. Now, here's just FCC in a different picture, so ABC packing. And an example of a defect is the stacking fault. That's the simplest example of a defect. Namely, instead of packing in the ABC fashion, you skip one of the layers. So these atoms should have been in here, but they moved into the A position. So instead of ABC as in the FCC lattice, you go to AB as in a hexagonal close packing lattice. So this would be a defect. This is a simple example of a defect. Now defects, there are more complicated examples of defects. And one complicated example is a line defect. So what would be a line defect? You take this crystal, you insert half plane of atoms, like this. So this is the plane join. So over here, that would be a defect. This defect comes out of the board, so that's a one-dimensional defect. Now, everywhere else, everything is fine, except here, something wrong is happening. Now, this is just a cartoon. Unfortunately, in nature, the structure here doesn't look this simple. For example, in the FCC example I just showed you, what is called the core structure here can be quite complicated. Actually, I think if you have the time, maybe I should not be imposing these things, details of these things onto you, but just believe me that the core structure is not a simple structure that I just described. It involves complicated atomistic description. And okay, so this is the one problem, namely the geometry side of the problem, that you have these lattices. Lattices have the hierarchy of defects, which are very tightly connected to the nature of the lattice. The second theme is the physics theme. One of the first questions is, why do particular lattices are selected? So now I use this one. So this is a periodic table produced by the youngest member of the E family. See, she's a 6-year-old. She wanted to get credit for doing this. So, and what's down here is color coding what lattice, when these elements at a very low temperature, they take a crystal structure. When they solidify, crystallize, what lattice do they take? So the blue are the BCC lattice. The red, the Republicans, are the FCC lattice. And the orange are the HCP lattice. And then there's another, there's green are the diamond lattice. The green are the diamond lattice. So first of all, it would be important to understand why these structures are selected. Notice that in here, in this column, everybody takes a hexagonal close packed lattice. It's not clear why the helium takes HCP, whereas the rest takes FCC. But they're close packed lattice. They're very close. They're very similar. Whereas if you look at the first column, these are the alkaline metals, they take BCC lattice. And then these green guys, these are covalent bonded systems. They take the diamond lattice. So this is the first question that one has to understand. This is the packing problem, but it's a quantum packing problem because the nature of the chemical bond, the nature of the interactions between electrons is important. So this is one of the first questions that one has to address. Secondly, and a related question is why solids are solids? So why atoms stick together? If you pull one atom, everything else goes with it. In physics, according to this is the sort of the cohesive force. What is the origin of the cohesive force? In physics, typically there are five. There's a classification according to the nature of the cohesive force. There are molecular crystals, which are crystals made up of these guys, inert gas atoms. They don't have valence electrons, so they look like hard spheres. So it's not hard to understand why they take FCC structure. And then there's the covalent bonded systems, which, for example, silicon example, and et cetera, metals, et cetera. So these are the two things one has to keep in mind. At some level, the things could be understood just in terms of geometry, but some other levels, you really have to think about the physics. Okay, now, what the questions do we need to address? So I already mentioned that one should understand the quantum packing problem, why certain crystal structures are selected for certain atoms. And the second question is to understand why crystals are stable. So this is the non-elastic regime. It could be nonlinear elastic, but this is the elastic regime. Why crystals are stable? Why don't they fall apart? And then third question, when do instabilities develop and then defects start to form, such as dislocations that I suggested in the beginning, earlier. And then defect structures of the defects, dynamics of the defects. If you bend a paper clip, why doesn't it fall? Why doesn't it break right away? That's related to this the dynamics of defect. And then the origin of plasticity, which is related to the defect interaction. So coming back to the theme of geometry versus geometry in the quotation, maybe in the quotation mark, versus physics, let me explain one thing, which is the gamma surface energy. So what is the gamma surface energy? You take a two-half crystal and you displace one with respect to the other by some amount, namely xy, and you ask, what is the energy of an atom on the surface like? So this function is important for understanding dislocations, stacking faults, some of these defects that I mentioned earlier. Now let me take an example. Again, the FCC lattice, and this direction, normal direction, is the 1, 1, 1 direction. Remember, in this direction we have planes of triangle lattices. So actually, let me think of an even simpler problem. Just take two triangular lattices and displace them and ask, what is the energy? Now, given the potential, you can write down this energy just as a lattice sum. So this is the lattice sum. Of course, a simple observation is that this function should inherit the symmetry of the lattice. In the case of triangular lattice, the point group can be written down very simply. It's the symmetry group, which is very simple, which is the generated by these three elements. One is reflection with respect to this axis, one is reflection with respect to this axis, and one is the rotation by 60 degrees. And this makes up a group of 24 elements. So gamma should have the symmetry of this group. Okay. Now, an easier way to implement this is to look at the dual lattice, look at the Fourier transform of this function. So the Fourier space, which will be the dual space, the dual lattice for the triangular lattice is also a triangular lattice. It's just looking, instead of looking like this, it looks like this. Okay, so it's also a triangular lattice, and the group acts also on that dual lattice. So therefore, in terms of Fourier transform, we can write down this gamma surface energy as in terms of just the orbits when you have this group acting on the lattice. And these Fourier-like functions are invariant on the group. And then, without knowing very much, you can take a function like this and truncate it and look at how it looks like. And when you plot functions like this, well, if you just show you that how the orbits look like, this is the first orbit, this guy is the second orbit, and the third orbit. So when you plot a function look like this is done by my student Jerry Yang. I hope he's in the audience. That's what you get. So this function, which is the gamma surface energy for this particular system, actually reflects a lot about the defects in the structure. Okay? For example, from this you can read that there are these partial dislocations, which I didn't impose on you. It was one of the pictures earlier. You see that the dislocation has to split in partials. You can explain the core structures of dislocations, stacking faults, and etc. And you can do the same for BCC lattice. I'm not going to go through that. But let's think about diamond lattice. So diamond lattice is something that I've avoided so far. Now diamond lattice is nothing but two FCC lattice, interpenetrating FCC lattice. You take an FCC lattice, which in this here what's drawn is the atoms of a one big cube. Looks pretty complicated. And you take this lattice, you shift along the diagonal by a quarter of the diagonal. You get this red lattice. The union of the two is a diamond lattice. In diamond lattice, what's important is that you have covalent bonds between the atoms. So if you take away all the atoms that's outside this cube, then you are left with fewer red atoms. If you look at this particular red atoms, it has a tetrahedron structure. It has forms covalent bonds with 4 of its neighbors. So this is the diamond lattice. It's the union of 2 FCC lattice. If you look at the 111's direction, it's also planes of triangular lattice. But diamond structures are very different. Silicon, carbon, etc., and germanium, they are very different from the typical FCC structure like aluminum. Right? If you take a silicon wafer and drop it, it shatters. It's a very brittle structure. And indeed, if you try to construct its gamma surface energy from some potential, it has much more structure. So here is the gamma surface energy in the 111 direction. The same kind of function I was plotting earlier for the FCC lattice, except this is for diamond lattice. And actually, it's probably better to show a blow-up of this. You can see that there's much more structure in here. And as a matter of fact, it's probably even better to show you the other picture. This is the surface plot. You can see it's very peaked. And the reason is because of the physics, namely in diamond lattice, atoms form covalent bonds. So the interaction is very much directional. It's like a delta function concentrated on particular directions. So in that case, you cannot get away by just looking at the geometry. You have to think about the bonding. Okay, so this is, do I have some more time? Okay, so this is sort of the introduction. So now let me try to get at least one theorem across. So let me look at the elastic regime. So here is also the connection with the institute. So how the solids, the first thing you think about solids macroscopically is nonlinear elasticity. What do people do in nonlinear elasticity? They solve problems of this type. I should get another sheet of paper. Okay. So this is a variational problem where V here is a function from a domain R3 to R3. And W is a function that determines the nature of the material. It's called stored energy density. F is some applied load, applied force, and V is the displacement. So you minimize this variational problem subject to some boundary condition and find the displacement field. So this is a rather popular way of studying solids from a mathematical viewpoint. 10 years ago exactly, actually, almost exactly, there was a special year here at the Institute led by John Ball on this type of problems. The question I want to ask is, where does this W function come from? So typically when people do problems like this, the W function comes from some sort of, rather ad hoc, you don't want to know type of procedure. So now here I want to ask a more fundamental question, namely, where does this function come from? And then indeed this question was thought about by Cauchy. So he thought about this problem. And then Born and Huang wrote a treatise 50 years ago and really laid down in the physics literature the foundation of the subject. So here's the Cauchy-Born rule, which is sort of a recipe in some way. So let's take this one-dimensional example. I have two types of atoms, the cross and the circle. So this is the undeformed, unforced situation. It's a lattice. And then you want to calculate what is the energy after it's deformed by some deformation gradient, A. A is the deformation gradient. That's the grad of V. Remember, this W function is where is it? Oh, yeah. The W function is a function of grad V. So V is a vector field. So this is the matrix. So A here is a matrix. In one dimension, it's just a number. So I calculate the following quantity. I take this lattice, a uniform deformed lattice, uniformly stretch or compress the lattice by amount A, and then displace the other atom. So the unit cell is this here. Displace the other atom by amount P. So then I calculate the energy according to some atomistic model. Could be quantum mechanics. Could be the Leonard-Jones type of classical models that I described earlier. So this is the function WAP. And then the Cauchy-Born energy density is just obtained from here by minimizing over this shift vector P. So now you plug in that here. So this is the continuum model according to the Cauchy-Bonne recipe. And then, of course, this is the original atomistic model written in a generic form. The question is, is this really valid? In what sense is this a good approximation to this problem, or is it? Now, in the last few years, this problem has not caught the attention of mathematicians for a very long time. But in the last few years, there's quite a number of work devoted to this. In particular, there was a meeting 3 years ago, maybe 2 years ago, at Princeton, where this sort of thing were discussed, and people would discuss counterexamples to the Cauchy-Bonne. So it looks like the Cauchy-Bonne is not valid, at least for some situations. I want to argue here that if you apply Cauchy-Bonne in the right setting, it's always valid. And here's the theorem. So there are two conditions. One is the two conditions are both stability conditions. The first, the stability condition on the continuum model, on this model here. So that's in the form of some sort of generalized Lejeune-Hadamard condition. The second condition is the analog of the first, except it's for the original microscopic atomistic model. It's formulated in terms of phonons. Phonon is a rather simple concept in solid-state physics, but it might take quite some time to explain what the phonons are. Okay, anyway, if these two conditions are satisfied, then you can show that, number one, the continuum model has a good solution. Number two, that the discrete model, the atomistic model, has a solution that's very close to the Cauchy-Bonne solution. Okay? Now, instead of going to the proof, let me just show you some pictures of calculations done by my student Jerry Yan. So this is the application not of the Cauchy-Bonne that I described here, but rather a modified Cauchy-Bonne for a popular problem, namely carbon nanotube. There are two pictures here. This picture is calculated by some sort of atomistic model using a tensor potential. And this other model here, this other picture is obtained by a continuum analog, a modified analog of the Cauchy-Bonne rule. So obviously you have to change something because this is now a surface. The Cauchy-Bonne as I described so far is just for the bulk. And this is a surface. You have to do something, modify that. Now, let me remark about the result. The result is sharp, namely that the conditions one puts on, if you violate these conditions, the Cauchy-Bonne is not valid. As a matter of fact, we've started to study. So the fact that Cauchy-Bonne is not valid is signatured by the instability of the crystal and also formation of defects. We have started trying to classify the instabilities and link that to various types of defect formation. And secondly, the result can be extended to dynamic problems. I discussed the static problems, but it can also be extended to dynamic problems. And thirdly, let me remark, there's a paper by Pierre Lyons and his collaborators where they also studied this problem. What they did is that they assumed that atomistic positions takes the atomistic position is given by a smooth function. And then plug into the atomistic model, look at the limit, and the leading order recovers the Cauchy-Bonne. So I wanted to take a remark at what's the difference between what we studied and what they studied. In this particular case, when you have just the simplest example of a linear Jones potential that I mentioned earlier, in 2 dimensions, looking at either triangular lattice or square lattice. Now, our result would indicate that for square lattice, Cauchy-Bonne would not be valid, whereas their result would not distinguish the two lattices. As a matter of fact, in the case of square lattices, the Cauchy-Bonne is not valid because the lattice is unstable, the elastic moduli is negative, things like that. So let me finish by saying that, actually I seem to be finished on schedule, that first of all, atomistically based mathematical theory of solids is both important and I also think possible, feasible. It's not impossible to do. And secondly, thinking in terms of geometry and also physics, the separate themes of geometry and physics is helpful. And I'll stop here.
Thank you, Weinan, for a very interesting talk. I think we have time for 1 or 2 questions. The question.
whether one could calculate the certain specific properties of solids, and such as specific heat. Well, certainly this is done routinely in physics, solid-state physics. But specific heat, thinking from a mathematical point of view, turned out to be a rather difficult problem. But as I say, it's routinely done. But if you look at a more fundamental level, that's a rather difficult problem. Yes. Pardon me? Oh, that's because the dislocations, Silicon is diamond lattice. So silicon, compare silicon to aluminum. Say, if you take a paper clip, it's bended, it's not breaking. Whereas you take a silicon wafer, it breaks. It's because the dislocations is very hard to move in silicon. So the reason that paperclip aluminum can sustain such a large deformation without being breaking is because the dislocations are very mobile. So they can move around in order to relieve the stress, whereas silicon doesn't have that option. Diamond is like silicon, yes. It's a carbon version of it. That's because if you didn't hit it hard enough, the bonds are very strong, but it doesn't have this, you cannot bend it around. It doesn't have.
Okay. So thank you, and once again, thank you for a very nice talk. Our next speaker is Fritz P, who is Professor Emeritus in the Department of Mathematics at the University of Bonn. He will speak on my joint work with Armand and Borel from 1952 to 1954.
Where's some chalk? Yeah. Well, it's a pleasure to be in Princeton again, and I will report about my joint work with Armand Borel in the years 52 to 54. We were both members at the Institute for Advanced Study. Now, our joint work has a title, Characteristic Classes and Homogeneous Spaces, and was published in the American Journal of Mathematics in the years 58, 59, 60. But actually, all this goes back to the time at the Institute. I present a selection in the terminology of the 50s. So this more than 50 years ago, in the first third of the existence of the Institute. And well, I use the old terminology and also the old methods, in particular writing on the blackboard. So I take a vector bundle E over the base space B, typical fiber Cn, and this vector bundle has a Chern class C of E, and it's a sum of the Chern classes in the individual dimensions. And the ice Chern class is an element in the 2-ice cohomology of B with integral coefficients. Now we can always assume that we have here the structural group UN, a unitary group, and this unitary group then allows us also to have a Hermitian metric in all the fibers. And so now we can take the flag manifold, which is a unitary group divided by the maximal torus, and this maximal torus consists of all diagonal unitary matrices. And of course, a point in this homogeneous space is an n-tuple of one-dimensional linear subspaces of Cn. And now it is possible to take the associated bundle with this flag manifold as fiber. So we can call this a flag bundle. So in this bundle, the typical fiber is this flag manifold. And the projection we call sigma. And now we lift our given bundle E to F. And now suddenly the bundle splits up into a direct sum of line bundles, so-called tautological line bundles, because over every point, if we take any fiber, this fiber is sitting over a flag, and this flag determines the splitting of the fiber into lines. And now we can take the Chern classes of all these line bundles. So we can call the first Chern class of the i's line bundle, we can call xi. And so this is in the second cohomology of the flag bundle. And then we can lift the total Chern class of E, and this is the same as the Chern class of the lifted bundle, and this then by the rules for Chern classes, which we assume known here, this becomes the product of the total Chern classes of our line bundles, and sigma star is injective. So whether to know C of E or whether to know sigma star C of E, this is equivalent. And suddenly the i's or the j's Chern class of the bundle E lifted becomes the j's elementary symmetric function. In the xi. Now here we are very close to the thesis of Borel, which was published in Annals of Mathematics, 1952, to consider Chern classes as elementary symmetric functions. And this is also very important to determine the cohomology ring of un over Tn. This is also part of the thesis of Borel. We can, you see these cohomology classes xi, they belong to the cohomology of F. The fibers of F are these flag manifolds, so we can restrict xi to a flag manifold. Over a flag manifold we have this Tn bundle, and therefore the n line bundles. So the xi restricted to the flag manifold are cohomology classes of the flag manifold, and I will also call them xi. And so then, therefore, I can take the ring over Z, polynomial ring in these x's, and now of the elementary symmetric functions in these x's, they come from the base B, and therefore they become 0 on the fiber, and so we can here divide by the symmetric functions in the x's of positive degree. So let's call this ring S plus, So in other words, all the symmetric functions of the xi are being killed, and this is exactly the integral cohomology of the Fleck manifold. Yeah, so this is of course a very interesting algebraic object. You take the polynomial ring in n variables and you divide out by the elementary symmetric functions in these variables of positive degree. Okay, so now in the spring of '53, I came to the office of Borel and told him some of my work. Namely, I wanted to study the tangent bundle of which I get as a bundle over F. Well, we cannot take the tangent bundle. B is an arbitrary base space, but I have the fibers in F of F. And now this F has a complex structure, natural complex structure, because instead of looking at n tuples of one-dimensional linear subspaces, I can take Flecks in the other way, that I take a one-dimensional complex linear subspace contained in a two-dimensional complex linear subspace contained in a three-dimensional one, and so on. And this obviously has then a complex structure. And then for each fiber, we can take the tangent bundle of this complex manifold. So this Fleck manifold bundle is fibered in such Fleck manifolds. And then we can take in every point the tangent space along the fiber. And then we get a vector bundle over F. And this vector bundle has, of course, as dimension the dimension of the Fleck manifold, which is n times n minus 1 over 2. The complex dimension of this Fleck manifold is n times n minus 1 over 2. And now the question arises, what is the total Chern class of the bundle along the fibers? Well, let's call this F with some triangle. I think we called it like this in the old days. The tangent bundle along the fibers. And this tangent bundle along the fibers also splits in line bundles. And we have to take this product. And so these are this many differences, xi minus xj. Yeah, so I went to Borel's office and said that I needed for Riemann-Roch proofs such effect that the total Chern class of the bundle along the fibers is given in this form. And then Borel looked at this and said, well, here we have the roots of un. And while I had proved this not by the theory of roots, but by some induction, because this Fleck bundle can also be obtained as a tower of projective bundles, and I had studied this problem of bundle along the fibers for projective bundles. Okay, and now this led to some general theory for compact connected Lie groups G. We can take, if it has a rank L, we can take G, the maximal torus has then dimension L, and we can take this, we can also call it Fleck manifold. And now the points of TL, T is a product of L one-dimensional spheres, and a point on a one-dimensional sphere can be given by an integer modulo 1. And so we have actually over this Fleck manifold, again, L line bundles, which correspond to x1 up to xl, to the coordinates we introduce on t to the L. And then the roots are certain linear combinations in these coordinates, x1 to the L, which we can obtain by the adjoint representation. And so these are the roots. And then the result, which is actually almost the definition of the roots, is that the total Chern class of G of t to the L is actually the product of the roots. The roots become the first Chern classes of certain bundles, line bundles over G over t to the L. Now you see these coordinate functions I mentioned, x1 up to xl in t to the L, they determine the line bundles over the Fleck manifold, and the notation is very abbreviated here. These x's I use also as notation for the L line bundles I have, and then these are linear combinations in the x's like these. Yeah, and then, well, I see I don't have very much time, and now there is the Weil group also operating here. In the case of the unitary group, the Weil group is simply all permutations, and there all the coordinates can be permuted, all the line bundles can be permuted. Also here we have the Weil group, and the Weil group is a group of linear transformations in the x's, and the Weil group permutes the roots, introducing certain signs. Anyhow, the roots are perhaps only defined up to sign if I don't specify the complex structure on G over t to the L. And the first Chern class, if I take any choice of signs for the gammas, then I have an almost complex structure on G over t, and I can take the sum of these gammas up to dimension m. M is the complex dimension of G over t. So 2m plus L is the dimension of G. And then the question is, when does this almost complex structure come from a complex structure? And yeah, what we observed, well, the specialists know this for other reasons, is that when I take this Chern class and raise it to the m's power and evaluate it on the fundamental cycle G over t, then I either get 0 or I get not 0. Yes. And in this case, the complex, almost complex structure is not integrable. And in the other case, it is integrable. It comes from a complex structure, and all these complex structures are related to each other by an operation of the Weil group. And now the question is, what is the value if oh yes, this, and put this very high up. This machine. So the question is, what is this other value? And in fact, in the integrable case, C1 over 2 to the m divided by m factorial is 1. Yeah, why is this so? Now, Of course, Borel and I said we now know the Chern class of G over T, and by some other following method, one also knows the total Chern class of other homogeneous complex Hermitian spaces and so on. So one can apply to these are all projective algebraic manifolds. One can apply to these the Riemann-Roch theorem, which I was going to prove. The Riemann-Roch theorem was already formulated. One knew exactly how the precise formulas in terms of Chern classes and so on were, but it was not proved. But we still could apply it here. Why not? And there is also the special situation that here all Pontryagin classes of this differentiable manifold G over T vanish. Pontryagin classes only depend on the differentiable structure. And if the total Chern class is written as a product of linear terms, then the Pontryagin classes are the elementary symmetric functions in the squares of these roots. And the Weil group operates by permuting the roots and introducing certain signs. But for the elementary symmetric functions of the squares, it is obviously so that then these are invariant under the Weil group. And as in this example up there, that we have the polynomial ring in the axis modulo the elementary symmetric functions. To calculate the in the cohomology of G over T, we can throw away the invariance under the Weil group. But the roots are permuted, and therefore the elementary symmetric functions in the squares of the roots all can be put equal to 0. But these are by definition the Pontryagin classes. And so now, since the Riemann-Roch theorem, as we heard before, is so complicated, it is so that I better write it down only for the case that all Pontryagin classes vanish. And then it is the following. If we have for projective, I proved everything only for projective algebraic manifolds. So suppose X is such a projective algebraic manifold with vanishing Pontryagin classes. And then let D be a divisor on X. And takes the holomorphic Euler number of X with respect to the divisor D. Well, I just say now that Riemann-Roch expresses this number in terms of all the characteristic classes. But this becomes very simple. Suppose D in H2 of X with integral coefficients is the cohomology class of the divisor. Cohomology class of the divisor. The divisor has topologically codimension 2 and determines the cohomology class. Then the holomorphic Euler number is simply D plus half the first Chern class divided by the dimension of X, suppose is M. So we take this to the m's power, divided by M factorial, evaluate this on X. That's the whole Riemann-Roch, as simple as this. If the Pontryagin classes are not vanishing, then you must multiply this with the roof expression in the Pontryagin classes. But this I can omit here, because this is simply equal to 1, the leading term. So now in the case of G over T, we can therefore take all the an arbitrary D in the two-dimensional cohomology of G over T and evaluate this expression. Now the first Chern class C1 of G over T is always divisible by 2. It's the sum of the roots. This reminds us already of Hermann Weyl. If we take it to the mth power, divide by m factorial, we always get an integer. So if we take an arbitrary two-dimensional cohomology class in G over T of dimension m, raise it to the mth power, divided by m factorial, we get an integer. So what are these integers? Now it is possible, these mth power evaluated on x, to write them in a different way. And then one sees that these numbers, cohomology class D in dimension 2 to the raised to the m power divided by m factorial, that these numbers are up to sign either 0 or they are the degrees of the irreducible representations of G. So suddenly Borel and I saw that these chi of xd, the holomorphic Euler numbers, have something to do with the representation theory of G. And well, this had to be investigated much further. We also did some in this direction. I don't want to explain this here now, but there was a great development between the academic years 52, 53, 53, 54. Among Borel saw André Weil in Chicago, and when he came back to the institute, he explained that one can actually, using the Riemann-Roch spaces for the divisors, get directly all representations of G, realize them in this way, and this became the Borel-Weil theorem. And also this was very much improved by Raoul Bott in the year 55, 56, where Raoul Bott and Michael Atiyah and I were both all in Princeton. And so Raoul Bott did much work on this and improved all this very much. And then finally, it was even possible to calculate the characters of these irreducible representations in connection with these general topological algebraic ideas. Namely, there was the Lefschetz theorem for the complex analytic case by Atiyah and Bott, and with this it was possible even to get the character formula of Hermann Weil, which is very close to the Riemann-Roch theorem if I don't throw away here the A-Roof polynomials, because this expression with the A-Roof polynomials in it, so the Riemann-Roch written down as it is in full completeness, is essentially then Hermann Weil's character formula. Well, these are the developments at the time, but Borel and I made many applications of these things, and I wanted to mention a few of them. So I have to cut out several of them, but let me say at least the following. Take the 2n sphere, S to n. It has a tangent bundle, and tangent bundle of S to n. And the characteristic classes of the tangent bundle are, of course, well known, because everything practically vanishes. But now our methods, of course, included also the following, that if one has a bundle and applies to it certain representation of the structural group of the bundle, to calculate the characteristic classes of the associated bundle using this representation. This is essentially the same as looking at the character of this representation. And so now this tangent bundle T admits also the spinor group. Well, it originally admits the orthogonal group as structural group, but also we can use a twofold cover as a structural group. And to this we can apply the positive spinor representation. So then we get a vector bundle, delta plus of T. And so now we want to calculate the nth Chern class of this vector bundle. And it turns out that this nth Chern class is exactly n minus 1 factorial. No. Yes, n minus 1 factorial. So on the other hand, the bundle over the two n spheres determines an element of the homotopy group pi to n minus 1 of the structural group. Now this has a very big dimension, this delta plus of T. So let's just write infinite unitary group. And now we knew that the nth Chern class of every vector bundle over the 2n sphere is divisible by n minus 1 factorial. Well, we knew it not quite. We only knew it up to a power of 2. So every vector bundle of the 2n sphere is a Chern class divisible by n minus 1 factorial up to powers of 2. And here we had now a vector bundle where the total Chern class is exactly n minus 1 factorial. So one could expect that perhaps this is the best one. It's always divisible by n minus 1 factorial, and this generates an infinite cyclic group in pi 2 n minus 1 of u. Well, one could also perhaps suspect, I don't think we did, that this is isomorphic to Z. Yeah. So now, later, in 1957, Bott periodicity was proved, and then it became clear that pi to n minus 1 of u is always equal to Z, and that this element, which occurred in the work of Borel and me, is actually the generator. Also, in our work at the Institute, we could also write down certain exact sequences, and one example is that came out is that pi 10 of u is 0 modulo a 2 group, modulo the class of 2 groups. And homotopy theorists had proved that pi 10 of u is equal to Z3. And then if you look in Bott's collected papers, it's reminiscences there. He speaks of the spirited controversy between the topologists and the homotopy theorists. And Raoul Bott tells the story that in one night he was sitting there together with Arnold Shapiro to clear up this difficulty. And that there was also John Moore, and he bet $5 that the homotopy theorists were correct. And at the end of the night, this was in 56, 57, it turned out that Arnold Shapiro and Raoul Bott had proved that pi 10 of u is 0. Yeah, this is the story. But in fact, of course, the Bott periodicity says that this group is 0 for all even dimensions here and is Z for all odd dimensions here. So through these papers with Armand Borel, we came a little bit close to the Bott periodicity, and we came very close to the Borel-Weil-Bott theorem. All this improved by Bott. Now, other examples of, maybe I show one exercise we did, then I stop. Namely, a nice exercise is takes the homogeneous space U4, U2, cross U1, cross U1. because we calculated also Pontryagin classes and characteristic classes for homogeneous spaces. And now you have this Grassmann manifold, U4 divided by so U2 cross U1 cross U1. And this has two complex structures, complexly group divided by parabolic subgroup and so on in nowadays terminology. But we said, yes, there are two complex structures on it. One, you say the following: the space of all flecks of type zero-dimensional space, contained in two-dimensional space, contained in three-dimensional space, contained in the four-dimensional space, the only one we have. Yeah, jump 2, jump 1 in dimension. Now we do it the other way. Jump 1 in dimension, jump 2 in dimension, and at the end, now jump 1. So these determine two complex structures on this animal here. Now the question is, as exercise, calculate Chern numbers. This manifold has complex dimension 5. So there is, in the first case, the interesting Chern number C1 to the fifth, evaluated on the manifold in question. So let's call it X. What is this Chern number? Exercise, this Chern number is 4,500. Now you calculate this Chern number for the second case, other complex structure on the same manifold. People didn't know about the invariance of Chern numbers if one changes the complex structure. C15 on X for this complex structure is 4,860. That is, you see, this, of course, now you can make many more examples and take all these Grassmannians with their different complex structures and compare their Chern numbers with each other. Yeah, we also calculated the Pontryagin classes of, for example, the Cayley plane, which were not known. The highest Pontryagin number for the Cayley plane in dimension 16 is 39. And if you take the Pontryagin class in dimension 8, square it, and evaluate it on the fundamental cycle, you get 36. So these are examples. And of course, there were many other things. We looked at all the possible definitions of Chern classes in the literature. There were exactly 7. We knew. And we compared them with each other because they were all usually with different signs. Up to sign, they're all fitted, but we identified them with the standard one we use all the time. Yeah, thank you.
Thank you, Fritz, for a marvelous talk. I think, again, we have time for a question or two.
But Michael, is it?
Not really a question, but comment. Not remarkable. When this controversy arose about the disagreement, Sayre said, what a glory it would be for topology if the first part of mathematics showed there was a contradiction. What do you consider topologists with this argument?
Topology was working my work with Borel. and characteristic classes and so on, all the modern methods in topology we had at this time, modern then, now more than 50 years old. And homotopy theories, I don't know how they worked. This is very complicated. But also, I think in the case of homotopy groups of G2, there was some.
Actually, that's how we Morse theory. You have a quite different view of this. Okay? And actually,
never thought of this. Yeah.
One more question.
For Kodaira,
Did
I
you
don't-
overlap when you were here in Princeton at the Institute?
oh, you mean that we met him? Oh, we met him all the time, yes. And I mean, when I arrived in Princeton, as I told this morning in '52, I worked almost in the heat of the summer. I came already in August with Kodaira and Spencer almost every day, and they explained to me how the situation was concerning holomorphic Euler numbers and the results in Paris by Katang and Serre and their own results here. They explained this all to me. Yeah, therefore this was my luck that I came into this business very fast. And then when the winter term of the institute started, Borel came, and I could study the characteristic classes with him.
Okay. Sure.
Yes, yes, this was also mentioned this morning.
Michael said it was saying. On the other hand, he wrote magnificently on the board,
Yeah, this was 55, 56.
and he would very slowly write formulas and also. What amazed me was that he would cover more across in an hour than the two of us who talk all the time.
So, once again, thank you for a wonderful lecture.